Yeah, I can see on your
Yes.
slide on my screen.
Great.
Yeah.
Okay, okay. So good afternoon. Uh, so this is the last session, and we'll begin with this presentation on the design and fabrication of additively manufactured filters for high power application. Before I begin, let me briefly point out some of the motivations behind the current research work. First, the conventional microwave filters obtained either by exact synthesis, that is commensurate lines, or directly by insertion loss method, involves cascading suitable microwave structures. So this repetition leads to sharp discontinuities, which will excite spurious modes and also affect the power handling capability. Also, as a result of classical synthesis methods at high power and frequency, we usually get structures with narrow flat sections. So this results in making the structure more prone to multi-factor breakdown. Moreover, the classical filter design methods employed for conventional structures, like with step-shaped geometries, when used for smooth shape filters, are not convenient for various reasons, primary being the requirement of long optimization process. Finally, one of the key requirements for future telecommunication demand is high data rate. So this necessitates a high bandwidth, which in turn requires the satellite payload like filters to be designed for high power handling capability. So with these key reasons behind the objective of our research work here can be defined. So we need to develop a novel design methodology based on direct synthesis. Direct in the sense that it does not require the use of any intermediate lumped element network models to design the filter. The design method needs to be oriented towards direct metal additive manufacturing through SLM, selective laser mentally. The reason behind targeting additive manufacturing as the fabrication method lies in its capability of easily fabricating complex geometries. So our synthesis technique will produce filters which will have smooth variations. These smooth profiled structures are not very suitable to be fabricated using conventional technique like CNC milling and so on. Moreover, the design methodology needs to be general in the sense that it can be implemented in any technology and for any causal and passive frequency response. The flexibility of the synthesis technique should also allow us to design not only filters, but also pulse shaper, matched filters, and differentiators, and so on. So with these objectives in mind, I would like to point out some of the salient features of the design techniques which we developed. As we are targeting SLM for additive manufacturing, our building direction will be vertical. That is, the structure will be grown along the propagation axis. So this has a few advantages. First, that it will negate the need for any support structure and will also help in maintaining the same build conditions. So if you have the same build condition, it also helps in improving the reproducibility of the fabricated structure, which you can say is one of the key disadvantage in additive manufacturing. So if we have the same build conditions, we can have better reproducibility. Another advantage is it will also improve fabrication accuracy, as staircase effects will be reduced since we are growing it vertically, leading also to lower surface roughness. Another key feature is that if the key feature of the design synthesis is that if the angles formed between the filter profile and its transversal plane are not high enough to be self-supporting. Usually it should be greater than 45 degrees. Then we have some independent design parameters which can be modified to make them self-supporting. Obviously, in that case, the length of the structure will be increased. Finally, as the design method needs to be general, it will support any all-pole transfer function. Moreover, the synthesis technique is valid for filters with very high rejection levels, which is of great relevance in rectangular waveguide technology, which we'll be using. Before I move on, I briefly point out the theoretical background. We mainly use inverse scattering technique to generate the coupling coefficients from a required specification, and then use the couple mode theory to generate the design parameters from the coupling coefficients. I'll not go into the details of this theory, but I'll briefly show you the general design procedure, the general flow of the synthesis technique. The first part involves generating the transfer function from the specification. So this involves obtaining the unit elements prototype in terms of their characteristic impedance. These unit elements are then interpolated to produce smooth profile. Using these modified unit elements, we generate the required transfer function. So here you can see from the modified unit elements characteristic impedance, that is Zi, we get the transfer function S1. Next, the coupling coefficients are generated using inverse scattering technique. So we get from S11, we get the Kz. And finally, based on these coupling coefficients, we can obtain the device parameters using the couple mode theory. So from Kz, we get the design parameter for, in this case, we get the varying height profile of the rectangular waveguide. You can see this will be the equation. Obviously, it shows the relation between the coupling coefficient and the height profile, which is B. Now, obviously, this synthesis techniques assumes the propagation of only the fundamental mode. And so we also developed compensation techniques to reduce the effect of higher order modes. This is the design parameters of for low pass Chebyshev filters, which we have fabricated, is one of the example. As you can see, we have kept a comparatively very high rejection level of 80 dB for the stop band of 40 to 15 gigahertz, which is supported by our synthesis technique. So based on the design synthesis technique which I have shown, these are the single mode results. It satisfies the specification with the manufacturing tolerances. However, when we do the full 3D simulation, we notice the effect of higher order modes. It gets coupled, and moreover, when we designed this, we saw that the maximum height was very large. So this was also a reason why we got the effect of higher order modes. And since the height was very large, it was not suitable for vertical fabrication. So what we did was we reduced the height of the filter, but to maintain the standard ports, we used the tapers. So this was what I was talking about, that even if our design synthesis gives us a filter profile which is not suitable for vertical fabrication, we have this method of introducing tapers to make so that the fabrication is in the vertical direction. So once we introduce the tapers, then we did the full 3D simulation. We get these results. Obviously, we have to do a compensation for the higher order modes. Here you can see the black dash dotted lines is the single mode analysis. This was the initial analysis. Then when we did the CST simulation without the compensation, we got the gray dash dotted lines. So this was the effect of the higher modes. And so finally, when we introduced the tapers, we got and with the compensation, we got the black solid line. So this was in the design procedure. And because our main focus was high power handling capability, we moved on to the high power simulations. This is the Spark 3D simulation of the filter prototype. As we can see, it supports a very high power of around 300 kilowatts. We have done this simulation keeping around 1 e to the power 9 electrons per meter cube. But even if we increase the initial number of electrons, the breakdown usually hovers around this 300 kilowatt region. I show you a short video to signify the breakdown location. In this one, where the input power is 300 kilowatts, we see that there is no breakdown till 100 nanoseconds. I kept this. However, when I increased it to 375 kilowatts, there is a breakdown. And as expected, it occurs near the minimum gap along the smooth profile. So somewhere here. So since we are satisfied with this, we finally went for the fabrication. So these are the fabricated parts. In the top, it is the pre-plated one. This was done using direct metal laser sintering, and the material used was the aluminum alloy, the AL-Si10Mg. The usual post-processing methods like sandblasting and the polishing of the flanges was applied, but there was no need for any support structures. So we did the final silver coating. And yeah, these are the results. It satisfies the specifications which we had in our mind. The inset shows the improvement in the passband after silver plating. So usually we got around 0.2, but with the silver plating, there is a marked improvement. And that's all. If you have any questions, feel free.
Any questions?
So I have a question from Jabir.
Yeah.
Go ahead.
Can you hear me? Oh, okay. So I'm just curious, did you mention your building orientation, or when you were printing your structure, did you print the whole structure in one piece, or did you?
One piece. I can I can show you. Let me, if I have it nearby. So this was the filter.
Mm-hmm.
So this was designed. This was vertically fabricated. So it was one piece. So I hope you can see it inside.
Yes, I can. Just what was your building orientation? Did you said you put it just as like this, right? Yeah,
it's a vertical. We also tested in a inclined orientation, but just for testing purpose, but for other prototypes. But this was supported vertically. There wasn't any problem with this.
Okay, and because it was kind of perpendicular to all the curves that you had, does this add any surface roughness to your structure, or was that quite?
No. This because we did it in vertical orientation. The surface roughness was. Oh, sorry. Yeah, so surface roughness was less compared. But actually I did not test. That's why I asked you whether did you test it anywhere, because to test it, I have to destroy it.
Yes.
So
I would
So-
expect like some kind of stepping to be appeared in the, in the propagation direction. So
there might
maybe.
be, there might be, but what we can say is that the effect is reduced compared to the slanted orientation.
Okay. Yeah. Yes. I agree with that. Yes. Okay. Thank you.
Welcome.
Maybe a question from my side. I don't know if I missed it or not. Did you do any post-processing inside before metallization?
Yeah, this was in the silver path. So this whole structure was submerged in silver path. So
yes, but did you do any post-processing on the metal inside before to make it smoother or anything like that?
yeah, the sand blasted, the usual sand blasting.
Okay.
But this was before metallization. Yeah, this was done by the manufacturer. We did not give any specification. They said, okay, we will do the sandblasting, which they usually do after having after having the fabricated part.
Could I jump ask question? So after sandblasting, so surface finish will be better, right?
Yeah.
So you already you say okay the tolerance and 100 micron somehow. So after and sandblasting, so what would be the surface finish? Or smooth?
I didn't get.
So after sandblasting, okay. So how smooth is that surface?
Oh, we actually because it is non-destructive. I cannot measure. I have not yet measured.